then maybe the data that you are seeing there are going to be independent of each other because it's only random type of noise somehow in that situation. So the typical assumption, which is not always the case by the way, is that these delta sub m, when you are in script m sub 0, are independent, and then it's also independent of this case. But inside the ones that are relevant, those decision functions need not be independent of each other. You have independence for those genes that are not relevant, but they need not be independent when you are outside that collection. Okay, so these are the minimal type of assumption that you have in here, but it's not always the case because you could actually put dependencies in this situation. Okay, now, next issue that comes up. So let's say that I give you a decision function delta. Okay, so I say, okay, this is the decision function that we are going to be using in this problem. Okay. Remember that the data x is random. So what we will see there is just one of those. Okay? You could be unlucky. Okay? The data that you saw might not be a very good data and you could be unlucky. So how do you evaluate things then? Now from the statistical point of view, we evaluate that by taking the average over all the possible data realizations. So you take the expectation of the losses. When you take the expectation of the losses, then you get what you call as the risk function. Okay, that's what you call as the risk function. It's the average loss that you will commit if you use delta, and then that data is governed by the p. Okay, so the way we are doing this is that the way we, in the frequentist sense, the way we evaluate the procedure is over repeated sampling. Of course, in the Bayesian paradigm, we don't do that. Okay, the data speaks for itself, and then that's how we evaluate that. But in the context of classical inference, for instance, the evaluation of the procedure is over the possible realizations of your data. And so that's the risk function. And then when you have this risk function R sub 0, that's for L sub 0, that is what you call as the family-wise error rate. If you have for L sub 1, when you take the average of this, that's what you call as the false discovery rate. That is the one that was introduced by Benjamin in Hochberg. And then when you take the expectation over L2, that is what you call as the missed discovery rate. Those are the averages of the errors that you could commit, okay, when you are using a decision function delta and so on. Now, when you take these expectations, these are with respect to the true probability measure that's governing your data. Of course, you don't know that. P is not known to us. Okay? So, but that averages is actually being taken over this P. Okay? What's the goal here? The goal then is to choose that multiple decision function delta such that these risks are small, whatever P is. Okay? Whatever that P is, we would like this to be small, we would like this to be small. Why? So the chances that we are making a mistake in our decision is as small on the average as possible for the losses that we are using to evaluate our actions. Okay, so that's the basic goal in this situation. And here's a kind of a simple, just to relate it to what we know in the classical statistics. If you only have m is equal to 1, that means that you only have one decision to make. Okay? Then what happens there? The theta is just 0 or 1. The action is 0 or 1. The loss functions are going to be this. Okay? Theta is 0, and then I give you 1, then that's an error. Okay? L2 is given by this one here, 1 minus a indicator. So this is going to be 1 if a is 0, but in fact you should have said 1. Okay? So that's the situation. And then x here, say, has a measure of probability distribution P, which might be taking values in P0 and P1. Okay, so two possibilities only. This is what we call as the simple versus simple setting. When you take the risks now for a delta associated with this problem, then R0 delta theta is the probability of declaring significance when in reality it is not. So that's type 1 error in our basic statistics. R2 delta theta is 1 minus this. So that becomes, notice that this is the probability that you will make the right decision given that it is actually significant. That's the power, okay? 1 minus that, and then, yeah, that. So consequently, that is the type 2 error. Probability of a type 2 error in classical statistics, when you have m is equal to 1. So what we basically did there, when you have now m large, the loss functions that we had is to combine all those actions that we are going to be taking. Okay, so it's a generalization of what we have. Now, for the moment, let's suppose in this case here that P0 and P1 have densities f sub 0 and f1. This could be both normal, possibly different means, for instance, or different variances. So the usual framework that we have. Now what do we do? Okay? So as I've said earlier, the R sub 0 is a type 1 error probability. The R sub 2 is a type 2 error probability. And then R2, as I had pointed out earlier, is 1 minus the power. The power is the ability to detect what needs to be detected as significant. Okay, so that's our power there. Okay, and so on. What's the desired goal in classical framework? We would like to control the probability of a type 1 error to say an alpha, which is your level of significance in our m equals 1 case. So we say, I'll give you a 0.05 level of type 1, okay? Give me the best decision that you could have. And the best decision is the one that will minimize the probability of a type 2. Okay, so this part is simply saying that the optimal decision that I wanted is something that controls the type 1 error probability, but makes the probability of type 2 error as small as possible. Okay, so that's what we call as the Niemann-Person framework of optimality in that situation. Now, for this case where m is equal to 1, we know this. Okay, all the students here knows this as the Niemann-Person lemma. Okay, in what we have there to get you the optimal decision, if you have those densities f1 and f sub 0, is the following. You're going to declare that there is significance, there is discovery, if the ratio of f1 and f sub 0 is greater than a certain value. You're going to declare that there is no significance if it was the opposite, and there's a potential that you need to flip a coin to randomize to get you exactly, say, 0.05. But you could ignore this part, that's the randomization part. But this is one of the main theorems that we have in mathematical statistics, that you could get the optimal decision by utilizing this, what we call as the most powerful decision function of Niemann-Person. Now, what you should observe though here, which we don't emphasize in our basic courses, is that this procedure actually depends on the alpha, the level of significance that you have given me. So this constant C actually depends on alpha, as well as this depends on alpha too. Everything there depends on alpha. If I give you a 0.05 level, if I change that to a 0.10 level, it's going to alter the test that you are going to use. So it's actually a function of alpha. And this is the clue to the whole problem of multiple decision problem, because that leads us to the notion of what we would call as a decision process. Okay, what is a decision process? To get into the more general problem. Okay, now a decision process now is simply the decision function that I'm using, but I'm going to look at that as a function of the level that you are using. So consider, for instance, the problem where I have normal data, x1, x2 up to xn, normal mu sigma square. I'm testing this hypothesis. Mu is less than or equal to mu 0. We'll call that as theta is equal to 0. And then mu greater than mu 0, we'll call that as theta is equal to 1. That's the one that we teach our basic statistics students in that case. So what do we do to test that? We use the t-test. Okay? This is the t-test. We say you are going to reject the null hypothesis if this t-statistic, where you have the mu 0 there, is greater than the critical value from the t. Okay? But what you would notice in this one is that the whole thing depends on the alpha. 0.05 level, that changes the thing. 0.10 level, that changes the thing. Now I'm going to look at this as a function of alpha. When you look at this as a function of alpha, you get what you call as a decision process. It's now a stochastic process that is indexed by the size, okay, of the test. Okay? So that's the decision process in this situation. In what do you want? The problem is that you would like the maximum type 1 error probability to be less than or equal to alpha. And then you would like to choose, under this constraint, the one that minimizes the other type of error. Okay? So that's the basic framework that we have. But notice that it covers all of those things there. Now, let's go now to the case where capital M is big. Okay? What do you do? Now, when you now have capital M big, then you have the notion of what you call as a multiple decision process. Remember, you have capital M decisions to make now. For each of them, you will have a decision process, which we'll call as delta sub M. It could be the t-test process. For the next one, you might have another process. It could also be the t-test process. For the third one, it could be a chi-square test, but it also depends on the size. So you now have a collection of multiple decision functions. We gather them into one big collection. We will call that as the multiple decision process. Multiple because now you have several of these things here. Okay, so our decision process for the M component then will depend on alpha, and then this is your test procedure like the t-test that I illustrated to you earlier. Okay, now what do we do in this situation? The typical approach here is this. We're going to pick a delta sub M from delta sub M at using the same alpha. You say, give me an alpha, and then I'll give you a particular alpha value, and then I'll just pick the test based on that. Like, say for instance, if in this one here, if I give you an alpha that is 0.05, then that's the test that we will use, and we will use the same type of test for all the rest. Okay? So you're using the same type 1 error probability for each of the tests that we'll be having. Okay? And this is the most popular one these days. And then you get into what you call, say, the Bonferroni or the CDAC. Now, remember that the problem in the multiple decision setting is that I'll give you a type 1 error probability, 0.05. Now, but you couldn't use 0.05 for each of the tests that you are going to be doing. Because if you do that, it will blow up your probability of type 1 error because of multiplicity. Bonferroni's rule, for instance, gives you that. So what you need to do to control your probability of type 1 error is to use a different alpha at each of the tests. And that will be, say, if you wanted to control it at Q, then what you need to use is Q all over capital M. So if you have 0.05, okay, Q, and then capital M is 40,000, this is going to be very, 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 very small. It's going to become very difficult for you to detect things there, okay? And the reason why we do that is because you want to control the probability of type 1. If you do not do that, then you don't have control on your type 1 error probability. Okay, that's one of the problems that we need to be very careful of when we have this issue of multiplicity. Okay, because it blows up on us. Just with 10 tests, if you use 0.05, then your probability of committing a type 1 is not 0.05, but it is already about 0.95. So no control at all. So you have to decrease that. Now, the other way that you decide on that alpha that you use for this, for instance, is called the CDAC. This is the case when you have independence, and then you could actually compute that, and then this is the particular alpha that you should use to pick the particular decision function at each of them. In that case, you control your error probability. Okay? Now, how do you implement this? So the basic idea here then is that you come up with a size function. Okay? The size function, that's a function of alpha, and then it tells me what alpha I should be using. I could have, for instance, a size function that goes that way. And then if I give you an alpha, I pick the value A alpha, and then that's the size that I'm going to be using. If you just have it diagonal, then alpha of 0.05 will give you a size of 0.05. But you could have a different type of function in this equation. And for instance, the Bonferroni size function will be given by this. The CDAC size function will be given by this. You gather now these size functions into a collection, and then given a decision process delta in a size function A, the way we choose the particular test to utilize is then delta evaluated at that particular size function. That's for one test, okay? Now, when you now have, though, this multiple decision problem, then what you do now is you will have a collection of size functions for each M. Okay? For M equals 1, I have a particular size function. M equals 2, I have another one, and so on and so forth. So this is now a multiple decision size function. You have an AM for each M, and then the condition basically here is that you must control it at, say, a certain alpha in that situation. Okay? Now, how do we proceed? If I give you a multiple decision process delta sub M, these are the tests